So for our last 45 minutes or so, we're going to talk about something way different than what we've been talking about, but actually kind of related if we got into it deep enough. We've seen some cases where we want numbers that are linked together. You know, for example, you might have a link between hours worked and the amount of, well, the amount of pay would be the obvious one. So let's say you work 4 hours, you get paid $36. So there's a relationship there. Or there might be a relationship between years that you've been on the job and the number of personal days you get per year. Let's say that if you've been on the job for 6 years, you get 4 personal days for the year. These numbers have meaning, and they have meaning when they're linked, even more meaning when they're linked together. I mean, each of them has a meaning separately. This stands for 4 hours. This stands for $36. They have meaning alone. But they have even more meaning when linked together because they show a relationship. Pairs of numbers like this are called an ordered pair. Like I said, each number has a meaning, but they have a meaning when linked together. And the order that they're linked, I mean, 6, 4 has a very different meaning than if I put 4, 6 up here. I mean, at 6 years, you get 4 days of personal time. That's very different than at 4 years, you get 6 days of personal time. This one's a much better deal. So the order matters. That's why it's called an ordered pair. Now the first number in these ordered pairs is usually what we call an independent variable. The reason for it is that's the one that can change on its own. Most often, if time is a part of this, time is most often that independent. Not always. Sometimes time can be the other one, but in this case, like years, 6 years on the job. Well, that's going to change on its own no matter what happens. There's nothing you can do to affect that. It changes freely. The second number is what's usually called the dependent variable. The dependent variable changes because it depends on its relationship to the independent variable. The amount of personal time you get per year depends on how many years you've been there. I said the number of years you've been there, that just changes with time. It changes on its own. The amount of personal time you get changes depending on that first number, that how many years you've been there. Or over here, the number of hours you work, that can be your supervisor or your whoever schedules you can change the number of hours you're going to work. It doesn't have to, nothing's going to affect that. But once the hours are set, the amount you get paid depends on those hours. So it's a dependent variable. Now this occurs enough in math where we have this relationship between two numbers, this link between two numbers, that we want to be able to represent it. And so far, the only way we've looked at representing numbers is on a number line. We've looked at a couple of different ways of representing numbers. I mean, we looked at the vectors. Like for 6, that would be a vector like that. The vectors are for math mechanics. If we are trying to add or subtract or even multiply numbers, we use the vectors because it allows us to work with the numbers. But if we're just trying to represent values and relationships, remember we had said one way to represent the 6 is just putting a dot at the 6. The problem with a number line is it's difficult to represent this link. We had the 6, 4 as one ordered pair. To represent that link between the 6 and the 4, it's tough to do. I mean, I suppose we could put a dot at 4 then show the link with a line and an arrow saying the 6 gives us the 4. And that's actually what they did at one point, but it's very, very clumsy. You can see it wouldn't take very long to really clog up that number line. So then they did, for a while, they tried, let's do 2 number lines. So they did something like this. Here's the 6, here's the 4, connect them. We didn't need an arrow there because we know the top line is the independent and the bottom line is the dependent. But again, you can see if there's a lot of ordered pairs, that's going to get cluttered up really, really quickly. So a long, long time ago, a pretty smart person by the name of René Descartes Descartes decided, let's take these 2 number lines and let's do this with them. We're going to set our first number line standard like this, just like we would any other old number line. And that's going to be our first number line, that independent variable. But then we're going to take our second number line, instead of putting it below it, we're going to go vertically with it. And now we're going to number the positive going up. And negative going down. And this is what's called the Cartesian coordinate system. Sometimes called the rectangular coordinate system because everything's in rectangles. So now to represent the 6, 4 ordered pair, what Descartes did is he went and he found 6 on, this is what's called the independent axis. It is the number line that shows the independent variable. And the 4 goes here, that's what's called the dependent axis. By the way, quite often, these are just called the x-axis and the y-axis. At the beginning level, a lot of times they use that term, but the technical term for it is independent and dependent axis. Well, we located those to show the link. What they did was this. We projected them up and over where they intersected. That single point right there, that red dot, represents a 6 because its shadow falls on the 6 on the dependent or independent axis, and a 4 because its shadow falls on the 4 of the independent axis. So let's say I put a point right there. What ordered pair represents that point? You can trace my kind of lines. Those should be straight. But that is, what does it trace down to on my independent axis? 3. And on the dependent axis? 8. That point represents 3, 8. What's that point represent? 5. And then -4. Remember that independent, or the x-axis, always goes first. What's this point represent? What's the first number? Careful. The first number would be -7. 4 would be the second number. That is the single biggest mistake I see people make is, they get the order, they mix up the order. When you're doing the location, it's always the horizontal first, the independent axis first, and then the vertical, or the dependent axis. So what's this point? -6, -7, good. Which one of those points A or B matches up with the ordered pair 3, 4? A matches up. Because that would be, I mean, I didn't do them perfectly, but has to be 3 would be first and 4. B would be 4, 3. The other way around. So we talked about these axes. This was the independent axis, the dependent axis, or the x-axis and the y-axis, however you want to refer to it. The center here, where the two axes or two number lines cross, is called the origin. Called the origin because that's where everything starts. Everything originates from there. That's the 0 point in both directions. Now you can see these axes divide my graph into 4 pieces. When you divide something into 4 pieces, it's called quadrants. This here is called the first quadrant, quadrant number 1. Over here, this is called quadrant number 2. The reason being is positive independent variable, positive dependent variable, that's always the first quadrant you use. So that makes sense to be the first quadrant. Now we talked about navigation and stuff for angles. If you're doing navigation, you go around counterclockwise. That's why this ended up being the second quadrant. What do you think this one is? Third and the fourth quadrant. Now again, I'm not terribly worried that you can find those points. But if I ask you what quadrant is this point in? Well, obviously 4, 3 is in the 4, 3 or 3, 4 are both in the first quadrant. But if somebody says, hey, the point is in the third quadrant, you know you can isolate that and search for it in there. What is the coordinate for this point right here that I just put on? It is 0, -4. Because on that independent axis going side to side, from the origin, I have gone over nothing, 0. So it's below the 0. Its shadow falls on the 0 on the independent axis. But on the dependent axis, it is a 4. Or -4, I should say. How about this one here? What's the coordinate of that point? -3, comma, 0. There it's at the -3 on the independent axis, but its shadow does fall on the 0 on the vertical. It has not gone up or down at all, so it's still at 0. If I give you an equation, x equals 3. Now remember, x is what we usually use for the independent variable. This is normally called the x-axis, y-axis. If I say that x equals 3, where does x equal 3? Well, is it over on this side? No. Over here, right there, x equals 3. Is that the only spot where x equals 3? Does x equal 3 here? Yep. How about here? Yep. How about here? Or here? Or here? Yeah. Anywhere along that vertical line, every point on that line has an x coordinate of 3. So whenever you just say, hey, x equals 3, it's going to give us a vertical line on the graph at 3. What if I say y equals -5? Same type of thing. Here's -5 on the y-axis, or the vertical axis, the dependent axis. But y is -5 there, 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 there. Every point on that green horizontal line, y is -5. So whenever you say y is -5, we get that horizontal line, or flat line. Now a little bit of a foreshadow into tomorrow. Something like 14 equals 3x minus 1 is something we've solved before. How did we solve it? Add 1. Perfect. So 15 equals 3x. And then divide by 3. So 5 equals x, or x equals 5. Well, how does that differ from solving this equation? How would we go about solving this one? Add 1, 9 equals 3x, and then divide by 3. So 3 equals x. Notice the steps in solving that equation were exactly the same steps. We just had a little bit different number. How would that relate to the steps in solving this equation? They'd be exactly the same again, aren't they? Add 1, divide by 3. This is what we call a family of equations. They're the exact same thing. And we can represent that whole family of equations like this. Instead of putting different numbers in over here, we just put in y equals 3x minus 1. It represents that whole family of equations. Now the problem is, unless we put a number in for y, we can't solve this to get a value for x. This symbol here, y equals 3x minus 1, represents an infinite number of possibilities. No matter what value I pick for y, I can find a value for x. Now, it's usually easier, simpler to pick values for x and figure out what the value for y has to be, just because it's less work that way. We're working forward instead of backward. The way we represent those solutions is on a graph. To figure out how to graph it, one of the first stages we can do is make a table. And when we make a table, what we do is we pick values for one of the variables. So I'm just going to pick values for x. So I might use -10. Let's think it's a little simpler on this side. Let's do -3, -1, 0, 1, and 3. I pick values for x. And then I have to figure out what y has to be based on those values for x. Now, normally you probably see tables that look like this. The x and the y are right close together. I put the y down here just to make room for some calculation here. Y is equal to 3x minus 1. So if x is negative 3, y is equal to 3 times negative 3 minus 1. What is that going to give us? What's 3 times negative 3? Negative 9. Minus 1? Negative 10. If x is negative 1, y is 3 times negative 1 minus 1. What's 3 times negative 1? Negative 3 minus 1? Negative 4. If x is 0, y is going to be 3 times 0 minus 1. What's 3 times 0? 0 minus 1 is negative 1. If x is 1, y is 3 times 1 minus 1. What's 3 times 1? 3 minus 1 is 2. And if x is 3, y is 3 times 3 minus 1. What's 3 times 3? Is 9. Minus 1 is 8. So what this is saying is on a graph, I can plot x is negative 3, y is negative 10. There is one point that's on that graph. X is negative 1, y is negative 4, negative 1, negative 4 would be right there. Well, these are really as ordered pairs. This is x is 0, y is negative 1. 0, negative 1 is right there. This is x is 1, y is 2. So 1 and 2 is right there. And this is x is 3, y is 8. So 3, 8 is right there. And had I drawn my graph well, and I didn't do too bad here, that makes a nice straight line. What does that line represent? Well, that line represents all of the possible solutions to that equation. If I put a dot here anywhere on the line, let's follow it down. There's x equals 2, y equals 5. That is a solution to that equation. When x is 2, y is 5. Any dot I pick, I could pick a dot right here. When x is 1/2, y is also 1/2. Should have been up here more, but anyway, you guys get the point. Any point I pick on that line, I trace it to its x and y coordinate, and it gives me a solution to that equation. Okay, well, I wanted to save a little time at the end of class today for questions on test 3. Anybody have any questions off test 3 that they want me to go over? I did get your message, Betsy. I will resend that to you too as soon as class is over, just so you get it. Okay, well, with that, then I'm going to end the recording here, and then I'm going to offer you an extra credit opportunity.